Hey, good morning, everyone. Can you hear me all right? Yeah, cool,
Yeah,
cool.
Yes.
yeah, it works.
And let's see, do we have Alexa here as well?
Yes, I'm here.
You.
Hello.
Hey, you want to say a few words of introduction, Alexa?
Well, if you don't want to do this, yeah, I can maybe. Welcome everyone to the next generation AGI architectures workshop. Well, the idea of this workshop came to us, Ben and me, when we started discussing a possibility to develop a new version of OpenCog or something like that. There were a lot of different new contacts with people doing something interesting in the direction of cognitive architectures and AGI, which we found in correlation with our own ideas. Initially, the idea of this workshop was to gather these people face to face and discuss in a lot of technical details the possibility to maybe to do some common research or just to share our vision. Unfortunately, this situation with pandemic and self-isolation and online conferences, it changed our plans a little bit. And we decided to do it like a more internal type discussion. But we still hope to discuss it in a wider way than we are usually doing this within our team. And although we don't have many external speakers, but we will have one. It's Kevin Wang. And after his talk, hopefully Ben will describe his ideas on general theory of general intelligence. And depending on timing, we will continue with different more in-depth issues on programming languages for new generation AGI architectures and so on. So maybe we can start with our first talk. As I mentioned, it will be Kevin Wang. He's a 15-year-old who is interested and passionate about AGI. He's done work with knowledge representation, causality, spiking neural networks, and he joins writing articles, programming projects, and learning about interesting things. Kevin is also an innovator at the Knowledge Society, a global accelerator for teenagers. Kevin will be talking about relational learning and knowledge representation with the Dora model, a symbolic connectionist architecture that is able to learn structured representations from unstructured examples. He will go into the basics of how the model works, provide interesting results, and a little bit about future work at the end. Kevin, can you share your screen and start your presentation, please?
All right, I'm gonna start sharing my screen. Thank you for the introduction. And before I also want to say a couple more thank yous. Wait, first of all, can everyone hear me well?
Yep.
All right, great. So first I wanted to thank Alex, who will also be joining me in the discussion period, He's the creator of the model, and I just want to thank him for answering my questions and having great discussions with me about Dora and AI in general. And I also want to thank Matt and Alexei for organizing the event and being very helpful as I was setting everything up. And okay, with that, I'll get into it. So when we talk about AGI, usually start by just talking about the current gaps that exist between current AI and then general intelligence, which is usually just human intelligence because that's the only example we have right now. And one of the main gaps that we like to talk about is generalization. So when we're talking about machines, right, a really famous example is Go. AlphaGo is very good at playing the game Go, but it can't really do anything else. And machines are just learning statistical relations between inputs and outputs, and they're just essentially curve fitting to whatever data that they're provided. And they're not able to perform in environments that are different from the input that they get. And this is, of course, completely different from what humans do. So if you take someone like Lee Sedol, who was the Go player that AlphaGo beat, he's not only good at Go, but he can also do a bunch of other things like humans can. And he could say like apply philosophy or war strategy, which are completely different from the game Go, and he can apply those concepts to his gameplay. So humans, right, are able to learn the relations between states in the world and then apply this relational learning, this knowledge to new environments. And this gives them the ability to generalize. In other words, getting an accurate mental representation of the world is a must and it's necessary for AGI. And so the question now is, how do we take these mental representations and formalize them for a machine? A good model that we have right now are something called predicates. So a predicate is just a simple representation that meets two requirements. The first representation is that predicates must be explicit and independent from their arguments. So if you take like a predicate statement like Sally is bigger than Bill, the predicate bigger than is independent from its arguments Sally and Bill. And you could replace the argument Sally and Bill with the arguments Joe and Paul, and that doesn't change anything fundamental about the predicate, and it doesn't change anything fundamental about the arguments. And then second of all, further expounding on the independence is that the binding between the predicate and its arguments is also independent. And this binding specifically is dynamic. So you could say that this cone is higher than this rectangle. And you could just break that predicate and say, no, that's not true. Actually, this rectangle is higher than this cone. And that statement, once again, doesn't break anything. And the predicate higher than is still intact. And the two objects also don't change as well. And so there are a lot of benefits to predicate-based thinking. When we think in terms of predicates, it allows for a lot more flexible thinking. So you can appreciate the similarity between relations like penguin and fuzzy cactus, even though penguins and cacti are completely different. So predicate-based thinking really allows you to make connections that might not be so obvious in the beginning. And in other words, this is basically just the textbook definition of generalization. Being able to generalize is being able to make connections between two things that on the surface aren't similar at all, but they actually have a lot of underlying similarities. But when we talk about the benefits of predicate-based thinking, we also have to talk about the costs. And there are difficulties that we encounter when we're trying to implement this type of thinking in a machine. And the main one being that these predicates aren't objects. They only qualify objects, and predicates only exist when they're describing objects. So if you take the predicate bigger than by itself, it doesn't make any sense. And it'll only start to make sense once you give it arguments like Sally and Bill. So once again, to further expound on this idea, that predicates are just fundamentally different from the examples we're learning them from. So as we're like exploring the world and gaining new information, this information is all concrete. So like we say, like this cat walks across the street, and these are concrete events. But predicates are more abstract representations of these events. So there's a little bit of difficulty to try and learn them just by looking at concrete examples. And the way we address this problem is with something called role filler binding. So what we're trying to do here is to constrain the problem to make it easier to solve. And if you look at a traditional proposition, a traditional relation, something like the table is bigger than the hammer, it's like this unified relation, and it's very hard to like come to this relation just by looking at the table and the hammer individually. So what we're doing with role filler binding is we're splitting this relation up into its core components, and are splitting it with role filler pairs. So if you look at this role filler pair bigger in table, the table is filling the role bigger, and then this role filler pair is bound with another role filler pair where hammer is filling the role smaller. And by linking together these role filler pairs, we're able to arrive at the original conclusion that the table is bigger than the hammer a lot easier. So role filler binding is really just reducing the problem so that we first learn these what are called single place predicates, which is another term for role filler pairs. And then we're learning more complex relations called multi-place predicates by linking all of these single place predicates together. And so this is the premise of Dora, which stands for Discovery of Relations by Analogy. And Dora is a symbolic connectionist architecture that learns structured representations or predicates from unstructured examples. And we'll see later on that the representations that it learns are very useful, and they model human cognition, human behavior pretty well. So just going over the basic architecture of Dora, Dora is a layered network of bidirectionally connected nodes or tokens. And the bottommost token layer is connected to a feature pool. So the feature pool acts as basically input for the model. And then the first layer is basically the object layer, which is an amalgamation of feature units. Second, or thirdly, I guess, each token is yoked with an inhibitor. So we'll see later on that this inhibitor is needed in order to, it's needed in the binding process, which I'll talk about later on. And additionally, each, the model itself is split into sets. So we have a driver set and a recipient set. And these sets are needed to, in the learning process, which I'll also talk about later on. And within these sets, they are laterally inhibited. So all the tokens laterally inhibit each other and compete to be the one active token in that layer. And then also within this model, there's a flow of activation. And usually that flow starts off from like higher layers in the network down into the feature pool and then back up into the other set. So the Dora model is not a feed-forward network like a neural network or any other algorithm. It's a steady state network, and it just keeps on running until we tell it to stop. And so the network starts off at this stable state where it's this like consistent rate of firing. And then eventually what will happen is the inhibitors yoked to each of these tokens that are constantly firing, they fire and they inhibit those tokens. And this is refraction. And so after this pattern is disrupted, the model starts to settle. What the settling process looks like is just activation flowing from the top here down to the features and then back up to the recipient layer. And this process is just repeated and repeated. And it is really in this settling part where the model is actually mapping connections and then learning. So let's take a deeper look into how this model is actually doing this. First, it starts off at the starting state where the model has retrieved objects from its memory. And once again, these objects are just a amalgamation, a collection of feature properties. So you look at, for example, something like a fire truck and an apple, and they have all these separate properties. And once the model has finished this retrieval process, it'll start to compare them. And at first, it begins to do this randomly. So it'll compare objects, and the shared features between these objects become coactive. And then in the self-supervised learning process of the model recruits two tokens to basically encode these coactive features. So you have one token on this object layer that encodes the role red. And then you have another token on this higher layer, which is the single predicate layer or the role binding pair layer, which basically encodes the role binding pair red apple. And so this role binding pair is basically a single place predicate. And to talk a little bit more about how this learning process works, this learning process is time-based. So the way that this featural overlap red is being bound with, say, this apple, is the binding information is carried by when these roles and these fillers fire. So if this RB pair was to become active, say, activation flows down from this role filler pair, and then these two tokens fight to become active. And the one that becomes first the order of this firing process is determined whether something is a role or a filler. And importantly, by requirements, this binary signal is dynamic. So it allows the same unit to be used in different representations. So like say this role red, right? It could be used in a different representation, let's say as it's describing a fire truck. The second thing I want to talk about is as the model initially starts, these single place predicates aren't relational. So these predicates are functional and they're connecting a role with a filler, but right now it's literally just the similarity between two objects. So for example, with this fire truck and apple example, fire trucks and apples are red, but they're also both shiny. And this overlap could also encode this shiny property. And this role red and shiny is not as useful as just the single role red. And so the way the model like sort of refines these roles is by detecting the relational invariants that exist within these predicates. So it will start to compare these roles and say the model will compare red and shiny with red and dull, and it'll see that red is the commonality between roles, and that will be a new predicate that is a functional predicate, but it is also relational, and it becomes useful as we build more and more complex relations. So after the model starts to build a bunch of single place predicates, it can then begin to learn more complex multi-place predicates, and it does this by linking co-occurring predicate sets. So what I mean by co-occurring is that when you're looking at a relational role, many of the roles they're relationally linked. Right? So if you see this ball, which is higher than this paddle, the ball has to be higher than something for it to be higher, right? So the ball and the paddle can't exist without each other in order for that relation to be true. So the way this like manifests in the model is that this RB pair encoding for the higher ball and this RB pair encoding for the lower paddle, they exist at similar time frames because they're relationally linked and they're co-occurring. And so the way the model begins to generalize this, and instead of just looking at a higher ball and a lower paddle and starting to come at the more general predicate where you could just have anything higher than anything else, it does this by comparing similar situations. So it'll start to compare, say, a ball that is higher than a paddle and a cat that is higher than a table. And it compares similar situations, and the similar single place predicates become coactive. Similar to when the model is learning single place predicates. And so we see here that the ball and the cat are becoming coactive, and the table and the paddle are becoming coactive. And through the same self-supervised learning algorithm, a new unit is recruited on the third layer to basically encode this higher order multi-place predicate relation. So if we're looking at how this actually looks like, you have a feature layer, right, that basically makes up objects. And these objects get bound together to create single place predicates. And these single place predicates get compared together and bound together to create these more complex multi-place predicates and these propositions, which is similar to what I was talking about earlier when I was just explaining the role binding process in general. And so this is just like a functional map of everything that's going on as Dora is learning these multi-place predicates, but I won't go over it too much right now just because of time constraints. And now let's just talk about the implementation of the model and the results that we've gotten. So something that's really cool and really interesting is that Dora and this architecture have allowed us to account for over 50 phenomena from the literature on human cognitive development, relational reasoning, and language processing. And another interesting application is Dora's application in game generalization. So the Dora model can learn to characterize game screens like this Atari Breakout game screen here. And then it can learn to play the game and then transfer its learning from Breakout to the game Pong. So it's able to do this with this process right here. So a visual preprocessor, which is just like a CNN or something, populates the feature pool. And then the Dora model is able to characterize game screens from this feature pool. And when I say characterize, I mean, Dora would be able to say something like, oh, in this case, the ball is higher than the paddle and slightly to the left of it. And this is really all you need to know. This is all the information you need to know in order to make a decision in the game. And so these representations which are basically very information dense, are sent into the reinforcement learning algorithm that is able to more easily train on them because there are less representations to train on. And if we look at the results of this experiment, we can see that Dora generalizes pretty well compared to a standard deep learning network. So Dora does okay, right, on the first few breakout games, but when it transfers to Pong, having never trained on it before, it does better than humans and way better than these DNNs. And then after it returns to breakout, it does a little worse, but it still does pretty good on breakout compared to the deep learning neural networks. And something else that is also super interesting is that Dora's learning path closely models the learning path of children. So if we stop the model at various points during the learning trajectory and then just use the knowledge it has at that point, we're able to simulate the developmental trends associated with children's magnitude reasoning and their relational shift. So looking at this table right here, we can see that an age 2 child is able to tell that two things are identical, but it's harder for them to tell that two things have a shared relation. And Dora also shares sort of the same property. And we can see this trend continues on as the child gets older and better at characterizing relations. So now in terms of future work and in terms of what we're working on right now. So one thing that we want to do is to integrate Dora with a neuromorphic model of vision. So like in the game playing context, Dora was basically just seeing through a standard CNN, and we want this model to be more accurate in how the brain actually works. Second is we want to incorporate meta learning into the structure. So we want to build an intelligent control structure that controls Dora's learning process. And with that, Dora will be able to basically learn faster and better. And finally, we want to incorporate reinforcement learning with the Dora's representations and Dora's relational learning. So right now, Dora is pretty good at representing the world around it. But the question now is, how do we implement these representations most efficiently? And that's what we're right now with like object networks and more reinforcement learning. So just to conclude, right, Dora is a symbolic connectionist architecture that learns structured representations. And these structured representations support generalization and transfer of both the representations and the policies learned. And finally, the Dora architecture mirrors a lot of phenomenon that we see in human cognition and behavior. All right, that concludes my presentation. Thank you.
Thank you very much for an interesting presentation. Any questions for now?
It'd be good to see a link to any papers or more detailed information on this if it hasn't been posted somewhere already. Maybe post in the chat function on the Zoom room.
Yeah.
Because it's the nature of everyone's AGI architectures is it's almost impossible to understand what the hell anybody else is doing. If you look at the papers and code, you can step a little closer.
Yeah. One paper here.
Okay, maybe I can have a quick question. So when you said that use CNNs to extract features, do you use pre-trained CNNs or do you train them end-to-end with your Dora model and reinforcement learning?
Yeah, so I think Alex, the creator of the model, can answer the question a little bit better, but just from what I know, the CNN is pre-trained and then we just use this pre-trained CNN to populate the features.
So thanks for your question. It's a really good one. So we're not as concerned with sort of end-to-end processing as some people in machine learning, because we're more interested in the sort of question of how humans learn to represent the world. And given that we know that, well, some people know that CNNs are not actually a very good model of human biological vision, we use these basically just as a proof of concept. So like Kevin said, we're currently a little more interested in integrating Dora with more realistic models of human vision and human object recognition. Yeah, but for now, you're absolutely right. We use pre-trained models.
Okay, thanks. So you take features from some highest level of CNN model pre-trained on ImageNet or maybe on Atari games or whatever. And how do you exactly construct the next level of representation? You said something about similarity. So do you just use a sort of L2 matrix to measure similarity between features or what?
No, that's another really good question. So basically, the model discovers the similarity based on the shared feature. So essentially, what the preprocessor, the CNN does, it's really like a mask RCNN that we use. But what it does is it identifies individual objects, and the individual objects basically consist of a set of features, which are the raw pixels, essentially representing the coordinate space of the object. And then so each object is fed into the Dora model as the list of features, which are the raw pixels that compose the particular object. And all of these raw pixels are sort of conjuncted by a token unit that says, okay, all these things go together. And then what the model does is it compares sets of these objects together, right? And then when sets of these objects, these conjunctive object units are coactive, they pass activation to their features. Any features that they have in common, like particular dimensional information, particular locational information, and whatnot, will tend to get more active than any unshared features, like their shape, maybe, or something like that. And so what the model then does is it learns explicit representations of these shared properties. And if you do this over and over and over again, what you end up with is explicit representations of shared properties that tend to be invariant in your training environment. So things like being bigger than something, being above something, being next to something, things like that happen all the time in these video game environments. Did that answer your question? Sorry if that was not clear.
Yeah, to some extent, but well, indeed, the devil details. We have had experimenting with visual question answering in also neural symbolic settings, and it creates a bias for me to interpret your model, and the lack of details also makes it difficult to understand. And as Ben put it, it's very difficult to understand any other cognitive architecture without first digging into the code. But in any case, I'd like to clarify some things now. Maybe it will be possible. So how do you represent predicates, and what algorithms do you use to learn them? Basically, there was an example with such a predicate as on top of, or something like that. You mentioned that you extract objects and assign some features to them, including spatial locations. So most likely these objects have coordinates on planes, so you can compare these coordinates, but there is such a huge space of possibilities of how to represent predicates, what predicates you can construct, and so on. So it's a very difficult question how to choose what to represent. Say, how do you choose that you can represent on top of predicate by comparing, say, y coordinate or something like that?
Well, you don't choose it. It just turns out to be learnable, right? So it turns out you can give a model like Dora these features, and it will learn essentially a representation that codes the invariance of being above stuff or the invariance of being below stuff, because it can then recognize aboveness, belowness, next to-ness in completely different contexts with completely different objects and in completely different sort of dimensional space, right? So you can the video game Pong exists in a different coordinate space than the video game Breakout, just by virtue of the way they work in OpenAI Gym. One is in portrait mode and one is in landscape. But so the choice of how to represent stuff is essentially what Kevin was talking about, and that's that initially the model just has objects which are like flat feature vectors, right? So they're representations, distributed representations in feature space that are linked together by some conjunctive unit, right? And of course, this is a simplification of what's actually, we know what's going on in your brain, but it's hopefully a useful simplification. These things get compared, and then subsets of these features are represented by different conjunctive units, right? So essentially, a subset of this initially distributed representation, a subset of the features in this initially distributed representation are represented as some new distributed representation encoded by some conjunctive unit. And if you do this over and over and over again, what you essentially get is different areas of the feature space represented explicitly and independently. And what turns out to get represented explicitly and independently is things that are invariant across whatever you give the model as experience, whatever you train the model on. So when you give the model a really simple environment like the game Breakout, which just has bricks and a paddle and a ball, what you end up with is representations of the particular objects that are involved, but also the representations of the very simple relations and properties that these objects have. They tend to be bigger than each other, smaller than each other, next to each other, above each other, below each other. Some of them are red, some of them are yellow. I think some of them are blue and some of them are green, but those are essentially all you can learn. If you train the model on something a little more detailed, like say the Clever data set, which is another simulation we did in this particular paper, you end up with more, well, still very simple, but I guess slightly more complex representations because there's things like texture in these particular images too. So what you essentially get out, what the model learns, is whatever's in the input and whatever's invariant in the input. We've done simulations of more sort of complex phenomena where we use sort of hand-coded inputs because we're trying to sort of represent human relational reasoning or human analogical reasoning. And essentially what the model can do is it can partition up an input space and explicitly represent aspects of this input space that are invariant. And whatever aspects of this input space happen to be invariant, the model will learn explicit representations of those things.
Well, yeah, it's nearly clear, but it doesn't answer to my question in full detail. What I meant is that predicates in general can be represented as arbitrary computational procedures, so functions, and you, I guess you don't enumerate.
I'm sorry. Yeah, sorry. I didn't understand your question. Okay, so the way that the model represents predicates is by virtue of the fact of how it solves the binding problem. So it solves the binding problem by using time. So essentially, the architecture of the model is such that when activation flows in a top-down manner, elements. Sorry.
No. It's not exactly what I'm trying to ask. I mean, you can compare numbers, yes. So you have a basic as some set of basic operations. You have comparison or something like that, which allows you to select a subspace of your feature space. DNNs use also some set of basic operations like weighted sums with nonlinear activation functions, and they can construct subspaces of our feature space and so on. So universal induction will deal with the Turing complete space of all possible transformations of these features or whatever. So you can have different computational representation of your predicates, and depending on this, you will have different capabilities of what invariants can be represented and learned. For example, when we are talking about this brick world, it's quite simple. We have coordinates, we have colors, we have simple shapes. You mentioned Clever, which has more complex features, but they're still quite simple. But if we have a much more messy world, like real world, and features which are not that distinctive, which form objects and their classes form very complex regions in the feature space. So will you able to really separate these subspaces which can have a very complex shape using your representation of predicates. So do you use just comparison operators to compare values of individual features, or do you have some computational procedures over the values of these features? I'm not sure if
no, that's sorry. That's a really good question. So there's a couple of questions, a couple of answers. One is, can the model deal with complex real world environments? No, it can't, because it doesn't have a very good visual front end, which is what we're sort of trying to work with right now. So one of the things that turns out to be true of human vision, as you sort of intimated, is that we can look at a complex scene, individuate objects, objects that from viewpoints that we haven't seen them before, and whatnot. Now, CNNs are notoriously bad at doing this, but there are computational models like Hummel and Biedermann's GIM model that are pretty good at that. So to the extent that we could integrate Dora with models like this, we might be able to deal with these more complex environments. To sort of answer your second question about what operations are available for computing aspects of the space, it's primarily the comparison operation, although there's an important thing which one question is, it turns out to be difficult to extract relational invariance from raw feature values. And so there's a couple of algorithms we've developed for essentially learning invariant representations across pixel space or across metric space. But those also are embedded in a process of comparison. So it's essentially comparison all the way down. And at present, we've had a reasonable amount of success with this particular operation for learning sets of relations, both simple and complex, for solving a variety of tasks. But of course, it's an open question how far this can go. So to the extent that comparison is insufficient for solving a particular problem or learning a particular subset of the feature space, our algorithm will fail.
Okay, thanks. It seems this is the answer to my question. And,
good, good.
Yeah, I have maybe a last question. It's about transfer learning in the reinforcement learning settings. So the results were extremely interesting. It's they indeed show the importance of this line of research and this sort of models, but the details were too brief to understand what exactly has been done to do this transfer learning. So I'm not sure.
No, that's a super good question. Super good question. So basically, what you'll notice about Breakout and Pong is, to us, they're super similar, right? So Breakout and Pong are incredibly similar games because all you have to do is follow a ball with a paddle. In one case, you have to follow the ball with a paddle on the X dimension, and in the other case, you have to follow the ball with the paddle on the Y dimension. So to us, to humans, the transfer between these two games is absolutely trivial. And it turns out it's also trivial for Dora, because all Dora needs to do is make an analogy between the move space available in Pong, which is left-right, and the move space available in Breakout, which is up-down. And if it's learned a policy, like follow the ball side to side, and it makes an analogy of side to side with up and down, it generalizes follow the ball up and down. So this is an incredibly simple case of generalization, or generalization within policy space. What we thought was kind of cool about this result is it's trivial for the Dora model, it's trivial for humans, it's incredibly difficult for these other deep neural networks, right? So as far as policy generalization goes, as we've demonstrated it in a very, 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 very simple space. But we think it's an informative simple space. The other thing that's kind of interesting about the generalization that sort of Kevin intimated is the generalization across representational space. So Dora uses the same representations, the same relations, to represent things like Breakout, Pong, but also reasoning tasks, analogical reasoning tasks that are given to children, right? So what's more generalizable is the representations that the model learns. And we think that's essentially what makes human cognition, or at least one of the things that makes human cognition unique in the animal kingdom is that we could learn representations across contexts that apply then across contexts, right? So aboveness and the representation of aboveness that you use is useful, not just because you learn it in the context of playing a video game or in the context of watching things drop when you're a baby, but then you generalize that particular concept to all kinds of different domains. So there's two sorts of generalizations that the model's involved in. There's the generalization in policy space and the generalization in representational space. The generalization in representational space is far more reaching. The generalization in policy space that we've demonstrated is really simple, but we think it's informative, right? And it's informative because it's a really trivial generalization for humans, and it's a really difficult generalization for deep neural networks.
Yeah, thanks a lot for clarifications. At least now I'm personally interested enough to dig into details, starting with provided link. Maybe some other participants have questions. I have a question. I hope you can hear me.
Mm-hmm.
For the binding problem, you mentioned that you use time. Can this be understood like a form of temporal happy and learning? So
yes, absolutely. It's completely temporal. So this is an idea we stole. Well, I stole from John Hummel, and John Hummel stole from Christoph van der Malsburg, right? So it's a very, very old idea of how binding can be represented in neural systems, and it's completely a temporal binding issue. Obviously, it's not necessarily the case that that's what human brains use, but we think it's a pretty decent candidate for what human brains might actually use to solve the binding problem. It's a useful source of information that it would be weird if your brain didn't make at least some use of.
I see. Interesting.
Yeah. So again, I'll stress that this idea is so old. It was proposed by Christoph van der Malsburg in at least 1980, probably before that. But anyway, yeah.
More questions?
Yes, hello.
Hi.
I have a question about reinforcement learning. Can your model use information from reinforcement signal to improve its representation of environment?
It's such a good question. In the work that we've described here, absolutely not. So the reinforcement learning algorithm we used was just tabular Q learning. It was super simple. Currently, I've got a student named Guillermo Puebla who's working on that problem of sort of integrating the process of reinforcement learning with the process of representation learning. And I think it's a really, really interesting and rich domain for exploration. As far as the answer, I embarrassingly have very little, other than to say, boy, oh boy, that makes a lot of sense. But I don't know how to solve that yet.
Thank you.
I have one more question. Do you also use some form of inhibition, or is it just increasing links whenever features reappear with each other?
No, you're absolutely correct. Inhibition plays an incredibly important role in the model. In fact, the inhibition signal is vital for establishing the sort of temporal patterns that carry the binding information. And it's so vital, in fact, that Bob Morrison and Lindsay Richmond and I have previously proposed that this essentially might be the development of inhibitory links between units in particular layers, so lateral inhibitory links, might be the, or at least a, important aspect in children's development of working memory. So the increasing working memory capacity that you see in children between the ages of about 0 and 7. But short answer is inhibition is a vital component. You cannot, at least I don't know how to get these particular temporal patterns without inhibition. In all the temporal binding models that I'm aware of that have been proposed, and there are at least 7 or 8, inhibition is a vital and necessary component. And again, we actually have proposed that inhibition might be the vital component in explaining the development of working memory capacity.
I see. And do you use a bidirectional form of inhibition, or is the link strength bidirectional
So can it be, for instance, that A inhibits B, but B does not inhibit A, so that the link strength.
Right now, all emission is bidirectional and equivalent. Now, again, like the previous question, this is solely a function of the fact that to the extent the problems that we've attempted to simulate, which are again simple problems, right? They're like analogy problems that kids solve, video games, things like that. This has been sufficient. I do not think it will be sufficient as we move forward. So relaxing this particular constraint and implementing it in intelligent ways is one of the future directions that we're looking at for work. So at present, we don't do that, but it will probably turn out to be really, really important. In fact, Bob Morrison, who I mentioned earlier, has actually made a proposal that one of the aspects in maturation, children's working memory maturation, is not just the increase in the inhibitory signal, but also the intelligent deployment of inhibitory resources. But I don't have a model of that. It's just a really cool idea, right?
Great. Is there also open source code available for this project?
Yes. Yeah, it's on my GitHub. I think Kevin threw up a couple links, but I can throw up a couple more. My GitHub is Alex Dumas, so ALEXDOUMAS, and there's multiple versions of the model for particular publications, and then there's a current version, which is our it's broken and it'll break your computer, it'll destroy everything, right? So don't install that at your own risk. But but it is open source and it's available.
Oh, wonderful.
GitHub Alex Dumas.
Okay.
Fantastic. Yeah, that's quite interesting. I look forward into digging in a little more depth, but it looks like a slightly different angle to the neural symbolic integration than what Alexa and I have been looking at, which looks like it could have some advantages.
Cool. Thanks. And again, I'd like to stress how impressive it is that Kevin is working on this part. Kevin's 15 and working on this particular project. When I was 15, I think I read comics. So yeah. So this is some pretty impressive work on his part, I think.
That's cool. Yeah, I think I graduated university at 18 myself a long time ago. So,
okay, so maybe you and Kevin, but certainly not me.
Yeah, I mean it's good to have a head start, and it's awesome to see you, Kevin, plunging into AGI among all the different things that you could have chosen to work on, because it's certainly not the easiest thing to bang your head against compared to a lot of other AI or software applications. But it's you're very lucky to be coming into AGI field at this time, because this is a time when everything is really starting to happen. So it's I think you'll have a good time and a productive career in the field.
Thank you.
So Alexei, should I give my brief presentation then?
Yeah, sure. It would be very nice if you give an overview of general theory of general intelligence.
Whoever is hosting this room needs to give me permission to share my screen.
Tim?
Yep, you're
all right.
You're free.
All right, is my screen now visible?
Yes.
Cool. Yeah, so we've just heard a really interesting presentation by Kevin and his advisor about a particular, cognitive architecture and what you call a proto-AGI system. And the situation in the field now obviously is nobody has achieved human level AGI yet, and there's different approaches which have different strengths and weaknesses. And this is just where the field is at. It's not a bad place to be at. And with the greater processing power and data and the software libraries for performing basic AI tasks, one can now more easily, get to the bottom line of what a certain architecture can do or can't do via experimentation, and look at the intersections between different architectures. And this sort of empirical work is quite valuable, and what I spent a lot of time on with my team in SingularityNET and OpenCog. However, I think it's also interesting to take a step back and think about the deeper theoretical basis of what we're doing with all these different AGI architectures. And if you take the analogy to flying machines, which is well worn and imperfect, but still there's something there. I mean, there's a lot of different ways to make machines that fly, right? There's machines that flap like birds, which actually work better now than they did a couple of decades ago. There's helicopters, there's airplanes, there's dirigibles, there's spacecraft. There's also fluid dynamics and aerodynamics, which is a general theory that underlies all these different types of flying machines. And of course, the Wright brothers didn't derive their design for an airplane using the Navier-Stokes equation of fluid dynamics. On the other hand, now the modern design of military aircraft is a mix of theory and experiment. And in the AGI context, we're egregiously matching. We're missing our Navier-Stokes equation, right? We're missing the equations of intelligence that underlie all the different AGI architectures, explain their different strengths and weaknesses, and give you guidance about how to build new architecture. So I've always been sort of divided in my mind as an AGI researcher as to, how much time to spend developing, designing, experimenting with particular architectures to see what they can do, sort of trying to be the Wright brothers, versus how much time do you spend trying to be Navier and Stokes and figure out like the basic equations of movement and structure of intelligence. Because better, if you understand the theory better, perhaps designing architectures can become a more straightforward process. So I've obviously been spending more time on the practical side, if you give practical a very broad definition, at least of spending more time on theoretical, conceptual, architectural developments related to building particular systems that do particular things, like the OpenCog proto-AGI engine, SingularityNET platform for making OpenCog and other AI systems decentralized and so forth. But in the background, I've been ongoingly thinking a lot about, what ingredients would you need to put together to create a general theory of general intelligence. And so what I want to talk about now for the next 20-25 minutes is I want to give a brief run through of some of the ideas I've been exploring in the direction of a general theory of general intelligence, and then explain how some of these ideas are guiding, sometimes loosely, sometimes more formally, guiding the work that Alexei and a bunch of our other colleagues in SingularityNET and OpenCog, the work that we're doing toward creating a new version of the OpenCog architecture. So yeah, to be clear, the theory that we're looking at here is intended to be, as general as we can make it. I mean, of course, if you have a mind 80 billion times as intelligent as humans, it may think all of our theory is completely primitive and ridiculous. But at least in aspiration, we're looking for principles of intelligence that can apply to human and non-human systems and to systems that are beyond the human in some sense. And there are various threads of inquiry we can draw on in creating a general theory of general intelligence. I mean, most participants here are already familiar with Marcus Hutter's universal AI theory, which is certainly interesting and relevant, and tries to solve the problem of, how would you make a system that could maximize computable reward functions in computable environments. And Hooder gives an algorithm that's about as good as anything at doing that if you give it enough resources. And that's interesting. I mean, there's the formulation of the problem in terms of reinforcement learning is arguably limiting in some ways. And there's a question as to whether what works with essentially infinite resources is that relevant to what works with realistic resources. But it's an interesting potential starting point for investigation. Of course, neuroscience is another potential starting point, and at least at the level of inspiration has proved valuable. Current neural nets have little to do with actual neuroscience, but they were inspired originally by neuroscience. But of course, neuroscience is insanely complicated. Like this little graph I'm showing, each of the little boxes is a different brain region studied by neuroscientists, and the links are connections between the brain regions. So there's a kind of specific architecture underlying how the human brain works at the intermodule level. Then there's so many neurons and neurotransmitters. So there's a lot of lessons to be gained from the human brain. And one problem is how to emulate what the brain does in a different kind of hardware, given our limited ability to image the brain right now. Another problem is extracting what's particular to the human animal from what is a general principle of intelligence. Cognitive science is another approach, and Kevin's talk that we just saw now is an attempt to sort of come to the computer science and practical AGI world from the point of view of human cognitive science, really, and looking at the different kinds of cognitive processing a human mind does. And cognitive science has isolated the different parts of a human like mind: long-term memory, short-term memory, perception, action, language, deliberation, metacognition, and so forth. And so even if you don't want to take exactly how the brain works as a guide for how an AGI should work, you could take the information processing characteristics of the human mind. We're going to hear in our one of the panel discussions on Friday of this conference from David Weinbaum and Kabir Vetas, have been working out a totally different way of thinking about intelligence. What could you think of as open-ended intelligence? Thinking of an AI not as optimizing a reward function, but as something that self-organizes, creates and processes patterns within itself and its environment, where goal functions and rewards are among the patterns that may pop up and then get improved or go away within the self-organizing system. So this is more looking at AGI as part of the study of complex self-organizing systems. So all these threads, all these points of view on general intelligence, I think are important. And these are all themes that I've pulled together in a series of fairly sketchy theoretical papers over the last decade or two. So I made a blog post on my personal blog, The Multiverse According to Ben, last month on the general theory of general intelligence. And pretty much that blog post is a bunch of links to papers published in various conferences and journals, and a couple I just posted online over the last decade, but just trying to explain how they sequence together and contribute together to an overall theory. And what I'm going to do now is spend a few minutes almost just listing some of the highlights of the ideas in those papers, because there's too much. I mean, eventually I'll turn that into a whole book once I have time to fill in more details. There's too much to go through in detail in a brief talk. So I will list through some of the particulars in those papers and then explain how those are feeding in our current design and thinking process as among the ingredients that we need to create a new open code architecture. So on a philosophical level, among other things, we could say an intelligent system, a mind, is a self-organizing pattern system that's engaged in recognizing patterns in itself and its environment, including critically but not exclusively patterns regarding the impacts that its actions tend to have. And it's not just recognizing, it's building new patterns in itself and in its own environment. Of course, the patterns it recognizes feed into the patterns it builds. And this high-level way of looking at things, of course, relates to open-ended intelligence and also explains how a practical system can optimize computable reward functions in computable environments. So what is a pattern? So this is in itself a complex, both philosophical and and technical question. One line of thinking I've been playing around with lately goes back to some philosophy and math work by Spencer Brown and Laws of Form, and a bunch of follow-ups of that work by Lewis Kaufman. And I'd encourage you to look at his website at the University of Illinois, some amazing stuff intersecting knot theory, quantum topology, and then sort of the phenomenology and ontology of perception and how the mind works. But the core idea that they have is we want to start with just the process of distinction. Start with the process of a distinction that distinguishes one thing from another, and they try to build up an entire model of the mind from distinctions of distinctions of distinctions, which is quite philosophical, but one can use this as a way to ground the concept of pattern, which is then something practical. So I mean, if you have a certain set of distinctions you care about, a certain set you don't care about, and then you have a program F that makes some distinctions among its inputs, meaning it maps some inputs into the same output and some into different outputs, then you can say that a program P or a process P, if you're looking beyond programs, a process P is a pattern of process F if P makes every relevant distinction F does, but makes fewer distinctions overall. And you can show that this definition, it's under some assumptions, it's equivalent to the algorithmic information theory view of patterns, which says basically a program is a pattern in a bit string if it produces that bit string, but is shorter than that bit string on the chosen reference machine. So we can generalize this to quantum computing. I'm not going to go over this for time reasons, but this isn't one of my technical papers for this conference, which you could find in the proceedings. You could look at distinctions that are weighted with amplitudes rather than being binary or fuzzy, and come up with quantum theories of patterns. And I was pursuing this line of thought partly because I've been thinking for a while about what would you consider a really natural underlying computational model for general intelligence. I mean, there's a lot of computational models that are equivalent under bisimulation in computer science, right? So you have Turing machines with their tapes, you have combinatory logic, and you have a whole bunch of formal languages, a whole bunch of other things that you study in theoretical computer science, and different ones are different for different reasons. And I was trying to go back to basics in terms of patterns and distinctions to see what would be a computational model that would be highly natural in terms of AGI. This paper, Combinatorial Decision DAGs, is in the proceedings of AGI conference, and I have a separate talk on this in the main AGI conference later this week, so I don't want to go in too much detail, but it feeds into the more general points I want to make, so I want to say something about it. The basic idea here is you start with a decision tree representation of a function, and this is not that weird. I mean, in computational complexity theory, you use decision tree complexity, the complexity, the size of the decision tree representation of a function as one way to measure the complexity of that function. But then I look at decision trees that are recursive in the sense that you can encode a decision tree as, for example, a bit string and feed it into another decision tree. So you have decision trees that make decisions based on other decision trees. And then you introduce a type of pattern-based memoization in a way, where if you have two sub-decision trees, and then you have you have a small process or a simple process that can map one decision tree into another one. So this decision tree doesn't have to be the same as that one, but it can be produced by some compact function from that one. Then you could replace a decision tree, say replace decision tree X with decision tree Y, well, with a function that produces X from decision tree Y plus a pointer to decision tree Y. So if you if you introduce that kind of pattern-based memoization and recursion among decision trees, then you get something that's pretty much like the SK combinatory logic on decision trees, and you get a different sort of computational model which has some interesting properties. So there's a there's a way of measuring entropy which is different than Shannon entropy called, that's not it, it's called, I don't have a slide for it, but let me explain it. It's called logical entropy. So the logical entropy of a partition is simply the percentage of pairs of elements that are put in different partition cells. So if you have a partition of n elements into 5 cells, there are n squared possible pairs of elements. What percent of those pairs are put in different partition cells rather than the same one? That's the logical entropy. And there's a generalization of that called graftropy, which is in a paper that I have on arXiv, which deals with the case of a subjective observer making distinctions between things. So in the case of graftropy, you don't have a partition, you have a distinction graph where two observations, for example, represented by nodes in a graph, they have a link between them if some observer cannot distinguish the two of them. So then a partition is a distinction graph which is divided into a bunch of disjoint subgraphs that are complete graphs. So the graftropy is just the percentage of all possible links between nodes in a distinction graph that are present in a certain graph. But anyway, what's interesting is in this combinatorial decision graph computational model, which I go over in my talk in the main AGI conference thread, if you make a program bigger, it doesn't decrease the logical entropy. And on average, bigger programs have higher logical entropy. So one of the math properties I liked about this particular representation in terms of patterns and combinatorial decision trees is there's a very natural, straightforward connection between the programmatic representation and the entropy if you look at logical entropy rather than looking at Shannon entropy. So I'll say more about why this is interesting a little later. And yeah, this was the paper on graftropy, which is on arXiv. So this connection between program representations and entropies is interesting and goes deeper, and it has to do, among other things, with the understanding of causality. Like one of the weaknesses of a lot of what's done in machine learning now is it's heavily correlative. I mean, you're finding patterns in data, and you're not in general seeing equally powerful ways of understanding the causal structure of data. And of course, there's a whole bunch of interesting work on that in the last few years. Most famously, Judea Pearl's ongoing fleshing out of causal networks and as a generalization of Bayes networks, but a lot more beyond that. Now, there's also some interesting work on algorithmic Markov conditions. So pretty much everything you can do with causal networks using probability theory and then information theory, you can also do with algorithmic information theory. So just as, say, in a Bayesian network, you want to know that's independent of its ancestors conditional on its parents. In algorithmic Markov network, you can look at a graph with bit strings at the nodes, where the bit string at one node has no extra compressibility conditional on its ancestors beyond its compressibility conditional on its parents, right? And so that's if you construct an algorithmic Markov tree like this, you can look at causality in a different way, where you can even infer, or at least you can hypothesize causality based on very, very few data points. And this relates to one-shot learning and few-shot learning and so forth, because to gather the statistics needed to make a traditional sort of Markovian network to measure causality, you can need a lot of observations. And if you can just look at mutual compressibility between bit strings or other computational representations and guess at causality that way, I mean, then you can make do with many, many fewer examples. I mean, of course, there's a lot more subtlety underlying that, but yeah, I had a paper on the maximal algorithmic caliber principle, which is similar to the maximum caliber principle, which is the temporal version of Jane's maximum entropy principle. So you can look at, just as natural systems tend to maximize entropy given their constraints, in some sense, do cognitive systems maximize algorithmic caliber, which is the generalization of maximum entropy to systems progressing over time, but to looking at entropies between individual observations rather than statistical ensembles. So there's a whole line of thinking there, connecting together statistical information with algorithmic information. And I think at bottom, when you sift through a whole bunch of annoying mathematics and cognitive architecture, this has a lot to do with the neural and symbolic connection, because a lot of what's being done with neural nets now is really statistical analysis. It's really information theory based, and symbolic systems, whether they're cast as logic or program learning or whatnot, these symbolic systems, they're doing things that are related to algorithmic information and compressibility when you dig down. So the relation between information entropies and logical entropies, and then algorithmic information, this relation foundationally tells you a lot about how neural and symbolic connect with each other. And I'll say more about that in a moment. I mean, I'm short on time, so I won't go through this in detail, but I had a blog post recently sort of looking at algorithmic Markov conditions and how these connect with decision theory. I mean, there's one of the many decision theories out there is causal decision theory, which says you should choose the action that will cause the best outcome for you. And there are various paradoxes associated with it. And I think many of them go away if you interpret causality correctly in terms of algorithmic Markov condition or its generalizations. I mean, you can also pursue similar math to ask, what sorts of, if a system, an AGI system, is viewed as pursuing goals, what sorts of goals should it be pursuing? And you can look at intrinsically which sorts of goals can most efficiently be pursued by an intelligent system, introduce notions of goal coherence. Say a goal is coherent if achieving that goal over a whole system is consistent with achieving the system's goal relative to the parts of that system. So like is achieving your goal over a long time period the composition of achieving your goals over the shorter time periods comprising that longer time period. So I think I haven't posted my thoughts on this yet, but I will later this week. They're sitting on my hard drive. But I just include this here to indicate that you can't really think about the goal is just something given and arbitrary, and then the AGI system is just trying to maximize an arbitrary goal. I mean, AXE looks at it that way. You can look at it that way. But I think there are certain symmetries and mathematical and conceptual properties of goals that make them sort of more copacetic to real world AGI and match better with AGI systems. So you can think about goal optimization as an important part of intelligence, but you then need to be thinking about properties of goals as well as properties of the optimizing system. So before briefly jumping into OpenCog 2.0. So one concept that comes out of all this is what I called cognitive synergy. And cognitive synergy is basically the idea that sometimes an AGI system may want to have multiple different representations of itself and its world, and then different learning algorithms correspond to these different representations. And then it needs good interaction between the different learning algorithms corresponding to different representations. So it needs, so when it gets stuck with learning regarding one representation, it needs to be able to invoke learning regarding another representation to get it unstuck, which requires sort of sharing of intermediate learning processing states between the learning algorithms working on the different representations. And why that's relevant? Well, one reason it's relevant is just because of the nature of the particular kind of intelligence that humans are. So human beings are pretty general intelligences, probably more general than like coffee cups or rats and so forth, but we're not maximally general intelligences. We can't run a maze in 750 dimensions very well, but we're not AXI. And some years ago, I published a paper called The Embodied Communication Prior, which had an intent quite similar to Yoshua Bengio's more recent paper on the consciousness prior. I didn't choose as sexy a name as Yoshua did, but I mean, I wanted to keep the qualia problem and the philosophy of consciousness off to the side, because what I was after here is what are really the biases that human beings evolved for. I mean, you can say being human, but that's too general. It seems like our general intelligence, it evolved for existing and manipulating solid objects in a world obeying certain kinds of laws of physics. We're not intelligent gas clouds in Jupiter. We're manipulating solid objects and breaking and composing them, and we're controlling individual bodies. Each of our minds is stuck in one body. What do these bodies do? Well, they manipulate solid objects. They move around, and they also communicate with other similar bodies that are controlled by similar cognitive systems. So I think the fact that our intelligence evolved for this communication among groups of similar minds in a world where the similar minds are manipulating, a shared collection of common solid objects that they can move around and manipulate. I think this has a lot to say about how general intelligence processes are kind of simplified into humanish general intelligence properties. And you can look at the situation that we evolved for, and you can see how the kinds of memory characteristic of the human mind come out of that. So you can look at semantic memory, procedural memory, sensory memory, attentional memory, and so forth. And these various aspects of human memory that are concretized in the human brain by different sub-networks specialized for those types of memory, these different types of memory, they basically correspond to different aspects of embodied communication, which is what we evolved to be biased to learn. But then these different types of memory correspond to different learning algorithms. And in the brain, when you say different learning algorithms, I mean, that can mean a lot of different things. It can mean different architectures within microcolumnar structure within different columns and different parts of the cortex. I mean, it can mean different distributions of different types of neurotransmitters and different sorts of synapses and types of neurons. In the OpenCog architecture, what it means is declarative memory and reinforcement learning, sensory memory, episodic memory. To an extent, we have different algorithms corresponding to these, and they all need to interoperate. So going back to the very beginning of this talk, what we're looking at in OpenCog is an architecture that is inspired by human cognitive science, less so by neuroscience. And within each of the sort of modules of mind identified by human cognitive science, like say declarative semantic reasoning, sensory processing, reinforcement learning, attention, episodic, within each of these modules that is highlighted by human cognitive science, I mean, then then we're trying to use computer science and math to figure out the best algorithms to deal with learning relative to those modules. And the cognitive synergy idea comes in the interoperation and common representation among these modules. So if you're using, say, a probabilistic programming method for procedure learning and a logic engine for declarative learning and reasoning, you know, how do these interact with each other? When the logic engine gets stuck, can it share its intermediate state with the probabilistic programming engine to help it get out of where it was stuck by translating the declarative learning problem into a procedure learning problem? Or when a neural net gets stuck on perceiving something, is it just stuck, or can it send elements of its intermediate state to a probabilistic programming procedure learning engine or to a logical reasoning engine to help it overcome its perception problem? And one can formalize this in terms of category theory, in terms of morphisms between the categories characterizing the different types of knowledge and the corresponding different types of processing, which is done in this paper from AGI conference. Looks like it was 2017, the one in Australia a few years ago. Now, this general theory of general intelligence, you could take in a bunch of different directions. I mean, if there's anyone out there who's really crazy, you could look up a paper I posted called Uri Physics, which tries to explain this, use this line of thinking regarding general intelligence in a very, very general philosophy of mind way, just to explain how minds work. But the direction I want to take in the last few minutes I have here before going to questions is just giving a clue of how all these abstract ideas are guiding our practical work on OpenCog. And I'm going to mostly leave this to discussion, but spend just a couple minutes going over some key points. So, I mean, OpenCog is one in a series of AGI systems that I've been experimenting with over the last few decades. The oldest code in OpenCog goes back to maybe 2001, although hopefully all the code I wrote has been removed and improved by now. I haven't been coding much for the last few years. We open sourced this in 2008, and the core idea here is to realize this notion of cognitive synergy by having a common representation among different AI algorithms that correspond to different types of memory. So the common representation is what we call the Adam space, which is a weighted labeled hypergraph knowledge representation, or you could more accurately call it a metagraph, because a hypergraph is like a graph where the links can go between many nodes. But here we also have links that can point to links, or links that can point to whole subgraphs, which some folks have called a metagraph. I'd call it a generalized hypergraph. But you have this common Adam space knowledge store, and then different learning algorithms corresponding to different types of knowledge all use this common Adam space knowledge store to represent their knowledge. And by working out the knowledge representation within this hypergraph appropriately, using the correct collection of type systems, you can get it so that when one algorithm needs help or needs acceleration, then the knowledge that it's represented in the Adam space can be transformed into the sort of knowledge in the Adam space that another learning, reasoning, or intelligence algorithm needs to help out that first algorithm. So we try to foster cognitive synergy among different AI algorithms by having the different AI algorithms use representations that overlap and are easily intertransformable due to using the same underlying Adam space meta representational fabric. And I mean, this can be used in more of a reinforcement learning vein. It can be used in more of a self-organizing systems, open-ended intelligence vein. And to get human-like intelligence, I think you need both. I mean, you need a certain element of goal-oriented activity where the system is trying to figure out what procedures will let it achieve its goals in the relevant context. And you need a certain amount of just ambient self-organizing learning where the system is recognizing patterns in itself and its environment without an explicit goal in mind. And OpenCog supports all these. It's been around a while, and we've been doing a lot of different things with it. We certainly haven't achieved AGI with it yet. We've been doing some prototype experiments of various sorts aimed at AGI, and we've also been using OpenCog within some narrow AI commercial applications, sort of buried on the back end, which has been interesting. And we've hit some obstacles in our recent work with OpenCog, which is pushing us toward, planning and designing a major rewrite of key parts of the system. I mean, it could be throw it all out, complete rewrite from scratch. Probably it won't be that, but there's going to be some deep improvements to various parts of OpenCog. Sort of tongue in cheek, we've been thinking of this as OpenCog 2.0, but that's a bit of a joke because the current OpenCog is more 0.2 than 1.0 anyway. But we've also been thinking of this as a true AGI engine, just because having a new name is nice. And I mean, there's a bunch of things that we need to do here. I mean, we need to upgrade the atom space in serious ways. We need to make the atom space as a body of code more scalable across many different machines and able to better exploit parallel processing on a single machine, and some more technical improvements to how types in the atom space work that I'll talk about in a moment. We need to better integrate modern deep learning frameworks and toolkits with OpenCog atom space, so that, among other things, you can efficiently and cleanly implement, for example, a common probabilistic programming framework across the atom space and across something running in, say, TensorFlow or Torch and so forth. And from revising the atom space, the common Wade-labeled hypergraph representation at the center of an OpenCog type architecture, I mean, that will imply some changes to the various AI tools that we have now working on the atom space. So the main goals of revising the OpenCog atom space are to make it easier to make the thing massively scalable. I mean, you can now run an atom space across many machines, but we have no feasible way to run it across like 10,000 machines. But clearly, you will need to do that to make an AGI. The scripting language we use for manipulating the atom space now has some problems with it, which are understandable given that it sort of evolved accumulatively over many years of use. We're now sort of scripting in a mix of Scheme or Python or C++ and explicit node and link operations, and we need something more coherent, where you're just using one language that the AI is using, which is cleanly transformed into one language that humans are using, rather than a mix of sort of Atomese and Scheme or Python or something. And yeah, we need to better integrate both neural symbolic interaction with external neural net libraries and meta reasoning, where you're learning about different node types and link types and type systems and so forth. And all these things could be done in principle with the current OpenCog atom space system, which is highly flexible, but at a certain point, it seems like it can be easier to go back and revise things. So one key element here is supporting probabilistic logic and programming better. And I don't have time to go into this much, but I mean, there's a lot of mathematical commonalities between what you do in probabilistic logic on declarative knowledge, like in our PLN probabilistic logic system, what you can do with probabilistic programming for automated program learning, and then what you do in probabilistic learning across neural net architectures, as you can see in primitive form in things like the Edward framework for probabilistic programming across neural nets, but you need to do much more general learning than these have done. So there's a common probabilistic learning framework you can see across program learning, logic, and neural net training and architecture learning, but to cash out that mathematical similarity in a scalable way that is suitable for real-time application and real-world experimentation, that has a lot of difficult implications for the infrastructure of your system. And OpenCog right now isn't up to that, but neither is anything else, actually. So, I mean, we've been doing a lot of work with neural symbolic integration. If you look at Alexei Potopov's paper on cognitive modules from a previous AGI conference, you see how in some ways you can go beyond just using a neural net as an input or output device for a symbolic system and deal with manipulation of, say, the processing graphs in a torch neural network and within various OpenCog nodes. But we need to go deeper in the integration, and this is both it's a software issue and a conceptual issue. And you'll see in one of my other co-author papers in this AGI conference, one of the many ways we're trying to make neural symbolic integration of work in a deeper way. Here we're looking at vector embeddings from an OpenCog hypergraph using an extension of the deep walk algorithm, and we're doing that now. But this sort of thing can be done, with more depth and more efficiency with some revisions to the architecture. Another thing I've wanted to play with for decades is algorithmic chemistry, which is like programs that rewrite programs to make other programs. And you can use an OpenCog atom space as this sort of underlying algorithmic chemistry infrastructure for a primordial cognitive soup of intermodifying algorithms, which can be an amazing way to foster computational creativity and feed new inputs to reasoning and learning algorithms. But again, I've tried to fiddle with this in current OpenCog code base. It's just very, very slow. So if we look at the high level architecture we want here, I mean, we have distributed atom space, which lives across many, many machines. We need a local cache atom space, which is something more like the current atom space. It works pretty well on one machine. You need some funky middleware to mediate between various local cache atom spaces and the distributed atom space. You're going from the distributed atom space to embedding vectors into symbolic patterns recognized by pattern mining. And we have a workshop on, among other things, pattern mining in OpenCog on the atom space in this AGI conference. Then we have an Adamese language interpreter, and this is one thing we're deep in the process of rebuilding now, which is a sort of native language of this atom space. And then using this Adamese language, you can either implement AI algorithms or you can implement appropriate interfaces to external libraries like neural net toolkits where AI algorithms are implemented. So, I mean, at the high level, this is more a software architecture than an AGI architecture, but it's a software architecture designed to implement the cognitive synergy-based AI approach that I've very roughly alluded to. So here, this is a list of questions from another of my papers for this AGI conference, and the paper is called "What properties should a programming language for an AGI have?" Right. So, and programming language is not the only thing we need to do here, but it's an interesting way to crystallize many of the broader questions. So what do we want out of an Adamese language, which can serve as the infrastructure via which all these different AI algorithms dealing with different kinds of learning on different kinds of memory update and learn from and grow this shared knowledge hypergraph? Then what should the language be on the surface level that humans could read and edit and write, but also what happens in the guts of this? And this is part of what led me to think about combinatorial decision graphs I was talking about 25 minutes ago, because you use combinatory logic deep in the guts of a Haskell interpreter and so forth. So the intersection of sort of combinatorial logic with pattern theory and simplification, which is what you see inside combinatorial decision graphs. These, I think, can be some of the structures useful deep inside the guts of an Adamese interpreter. But then it gets quite subtle. When you think about type systems, I mean, clearly you want dependent types, and you probably want linear types, which take into account resource utilization, and you want probabilistic types. But given that we still don't really know how to build an AGI yet, we can't expect to find one dependent probabilistic linear type system to rule them all and just wire it into the atom space. It's going to have to be more like different learning algorithms dealing with different types of knowledge have different type systems which are especially corresponding to the types of learning reasoning that they need to do. And then the atom space has to be a sort of meta infrastructure that lets different algorithms have different type systems that can interact and be refined in the course of learning. And this leads you to a sophisticated sort of gradual typing. So you need Adamese to be a gradually typed language supporting, probabilistic and dependent higher order types. And this is quite interesting because gradual typing maps via Curry-Howard correspondence into pair-consistent logic, and our PLN logic is a pair-consistent logic, which a probabilistic pair-consistent logic, which may be suitable for reasoning about this type of gradual type system that we want to use underlying Adamese 2.0, which is an interesting sort of metacognition. Now, doing all this super fancy probabilistic functional programming stuff doesn't seem like it could be efficient at all. I mean, the saving grace is sort of the programming language execution may not be the slow part, because getting knowledge in and out of a massive distributed hypergraph may be even slower, so that you can afford to do some fancy stuff in the language level. But anyway, these are hard questions which we're wrestling with now. And it's interesting, these are really quite different questions than the ones people are wrestling with in the corner of the AGI world, where they're looking at, how do you scale up deep reinforcement learning networks over as many machines as possible to play video games or to simulate understanding of natural language in a system that doesn't really understand it. So I mean, we're proceeding here from what I think is a pretty thorough and sophisticated theoretical understanding of what general intelligence is, what human-like general intelligence is, as a sort of specialization of more fully mathematical general intelligence. And then how would you build an algorithmic framework that could efficiently encompass the diversity of learning and reasoning that you need to realize human-like general intelligence within feasible resources? And we certainly don't understand everything that we need to do this, but this is a snapshot of some aspects of where we're at now anyway. And I apologize for going on too long as I usually do. I was talking as fast as I thought I could and still be understood. But yeah, let's move to questions and discussion now.
Sorry, can you hear me, Ben?
I do now.
Okay, good. Oh, sorry. Thanks for a really interesting talk. I was wondering if you could just give me a little bit of bit more detail on the neural symbolic interface stuff that you're currently talking about. Is this like hybrid architecture type thing, or is this implementing symbolic representations in a traditional neural network type structure?
It's a hybrid architecture. Okay. So there's several aspects, but if you look at Alexei Potapov's paper on cognitive module networks, which was a couple years ago in an AGI conference, then that goes over some key aspects of it anyway. So it's a hybrid architecture, but again, the two sides of the hybrid have to be able to see at some level something of each other's internal representation. So it's not just a black box where input and output are emitted and shared between the two networks, but nor are we necessarily trying to do neural nets within a symbolic system, nor to do symbolic stuff within a neural system, although you may have to verge on that also.
Well, in fact, Anatoly Belikov, Vitaly Bogdanov, and me will have a tutorial on neural symbolic integration in OpenCog tomorrow. So if you are interested in details, you are welcome to join.
Thanks.
By the way, a shallower comment about this Zoom meeting is if anyone wants their beautiful smiling face to be seen on the the live stream or video recording here, you can activate your video when you're talking, which I have been doing, but I think now this will be me talking to a bunch of static images, which is fine too.
All right. Are you planning this as a homogeneous calculation infrastructure, or you see this as distributed in different places of the world if you're looking for so many computers?
Definitely distributed and probably also decentralized, which ties in with the SingularityNET stuff I've been working on, right? So, I mean, one of the key things driving our desire to re-architect the atom space as a like infrastructure for weighted labeled hypergraphs is the current atom space is really single machined in its design. I mean, we can use multiple atom spaces with a common Postgres backing store now, so we can do on multiple machines, but we have no one ever thought through the atom space, you know, with a view toward modern scale distributed computing, just because it's old code and old design. But then decentralized design is a different thing, right? Like what if you have multiple different distributed networks, each running an open cog system, maybe owned by different people or something, right? And that's a sort of problem the SingularityNET decentralized AI infrastructure solves some of the mechanics there, although there's a lot of other tricky unsolved problems. But yeah, I think in the end, it's going to be a decentralized network of distributed systems. But that's, in terms of implementation, there's a lot of pieces to be assembled to make that a reality.
I assume you start with the smaller infrastructure, like heterogeneous in one calculation center.
Well, we have, yeah. I mean, we've been doing a lot of work with OpenCog now, which is either one machine or like a hub and spokes model, right? So then, yeah, when the Atomies 2.0 project is more mature, then yeah, we'll start with a single computation center. But then there's a parallel thread of work within SingularityNET of just how do you get different AIs to effectively coordinate within a decentralized network. So in the ideal world, those two parallel threads can intersect, like distributed OpenCog and SingularityNET decentralized AIs in general, and those two threads can intersect and get you distributed / decentralized OpenCog. But I mean, there's a huge amount of computer science as well as implementation in all these things that is yet to be done.
Okay, thanks. Sounds exciting.
When it works, it'll be very exciting. Yeah.
We have a question in the chat from Valerio. In which problems would you test cognitive synergy? What's your recipe for controlling different processes?
Yeah, so for testing cognitive synergy, I mean, the areas in which we're testing and evaluating this are, driven as much by contingent matters as by fundamental matters. I mean, we're looking a bunch at bioinformatics now and at medical hypothesis formation. So we're using OpenCog combined with the various machine learning tools. I mean, neural nets, but also evolutionary learning and XGBoost and so forth. So we're using OpenCog's symbolic reasoning and pattern mining together with machine learning algorithms to look at issues like how can you do precision medicine in a way that spans multiple clinical trials. Like if you're trying to figure out which drugs or which combination of drugs will work best for which people based on a single batch of clinical trial data, you do that fairly well using machine learning. On the other hand, if you want to come up with rules that translate and transfer from a body of existing clinical trials to a different clinical trial, which has different but related drugs or a different makeup to the patient population, this is a tricky transfer learning problem where you may have very high dimensional genomic data about each person in the trial, but only hundreds of people in each trial, but each of them has tens of thousands of genes, right? So you have a very tricky transfer learning problem. And we're looking at cognitive synergies between sort of sensory pattern recognition, procedure learning, and then logical reasoning in this context of transfer learning among biology data sets. And that, I wouldn't say that's necessarily a uniquely good place to be exploring this. It's interesting because there's clearly a lot of structure to the data, and the data sets are small enough that a traditional machine learning approach runs into trouble. The other area we're looking at a lot at the other end of the spectrum is robotics, and we're currently deep in discussions with the Hanson Robotics about some potential new collaboration projects with SingularityNET, OpenCog, and Hanson Robotics, and that's quite different than the medical case because it's so real time, right? I mean, you got vision and audition and movement data coming into the robot in real time constantly, and you have to come up with the best response you have in time for the robot to do something. But that has the strength that it's much more similar to what the human mind evolved for, right? I mean, the body of a robot like Sophia has many shortcomings compared to our human bodies, but still it's got many of the same senses, and it's dealing with a mix of goals on the same time scale and so forth. So that's certainly an interesting domain, though there's a high overhead in terms of the robotics to be doing anything. But we're also, just in the last month or so, we're reinitiating work on stuff we did in 2011 through 14 on just controlling very simple game characters in a Minecraft type environment. So just have a few different agents collectively building stuff in the Minecraft type world to play Go. We've been looking at OpenAI Gym and their Minecraft like implementations in there. I don't think you're going to get to AGI at the human level by fiddling around with toy agents in a Minecraft type world. We're just looking at that because we wanted a simpler environment just to experiment with the interoperation of different AI algorithms. Whereas I think that the bioinformatics and the humanoid robots domain are both rich enough that you could really use those to ratchet up further and further toward human level AGI.
Maybe we can have the last question with a long answer. Jeffrey on our YouTube live stream asks, how best can we address recursive reasoning and learning for creating and attributing relationships between nodes to inform and optimize decision trees and their associated causal impact insights?
Do you want to answer that one, Alexei? Yeah, I mean, that parsing through that sentence, it's mostly equivalent to how does advanced reasoning and learning work in the AGI architecture, I suppose. And we are, in a system that has logic as a significant component, the recursiveness, like the meta aspect of learning and reasoning, is not that hard to come by, right? I mean, in higher order logics and so forth, reasoning about reasoning is sort of par for the course. The issue is more, how do you control and guide this highly abstract learning about learning and reasoning about reasoning that logic systems let you do? And that's where the cognitive synergy comes in, because I think the sub-symbolic type methods are very useful for guiding attention and for learning control heuristics for the symbolic method. So in the OpenCog type approach, the recursiveness of representation and meta reasoning sort of comes with a logic representation, but then to avoid horrifying combinatorial explosions, then you need to do machine learning across the history of attempts at recursive reasoning and see what has worked or not. And this, my oldest son, Zarathustra, is working on this in the automated theorem proving domain. We have a theorem prover generating a bunch of math proofs, and you do machine learning on what the theorem prover does to try to learn optimal theorem proving heuristics. What we're doing is analogous to that, but it's in sort of uncertain common sense reasoning rather than crisp math theorem proving. There's an interesting, how do we align goals within a single AGI instance? How do you identify and correct goal anomalies? Well, I think in the OpenCog architecture, as we envision it moving toward AGI, I think we want to go beyond the idea that goals are this fixed thing created by the programmer in some external language, and then the AI system is adapting flexibly to realize these fixed and well-defined goals provided by an external, human overseer. I mean, there's a lot of writing on the pathologies of that approach and the ways that it can lead your AI to misinterpret the goals in various ways. So, I mean, in the end, goals are important, but the reinterpretation and the updating and revision of your goals, I mean, that's part of learning, and it's part of development that happens over a mind's course. So really, the goals have to revise themselves and improve themselves along with the rest of the mind. I mean, it doesn't mean that goal pursuit isn't important to think about separately. It means that reinterpreting the goals is just part of thinking and being the mind, and so optimizing the goals is just part of thinking and existing. So I really look at pursuing goals and then modifying goals as part of the self-organization of an open-ended intelligence. I think looking at a mind as doing reinforcement learning to optimize a fixed goal is going to be a dead end for AGI. I mean, of course, RL systems can do more specific things in hardware control and so forth very effectively.
In fact, I have prepared a presentation which doesn't really answer the question about the recursive reasoning, but gives some hints about it. But we have already run out of time, and instead of this, maybe it would be interesting to answer the last question, even it is not really related to our current topic, but seems to be rather important. How can a machine learning engineer in industry get involved with the SingularityNET?
Well, that is a question interesting to me, generally speaking, although not entirely pertinent to this this session on new AGI architectures. I mean, SingularityNET is a decentralized framework. It's for different AIs to talk to each other, share information with each other, and provide services on a marketplace. And it uses blockchain as the basis. So there's no centralized owner or controller. So much of the reason I wanted to build SingularityNET was to ultimately be the underlying infrastructure for a decentralized and massively distributed OpenCog AGI mind. On the other hand, SingularityNET as an organization, I mean, we're creating a marketplace for AI services, which can also be narrow AI services. Most of them on there are now. It doesn't have to have anything to do with AGI. So, I mean, if you are developing AI algorithms or products that use AI algorithms, and you want to put them out there on this decentralized AI marketplace, I mean, there's a tool called AI Publisher that you can find linked from SingularityNET.io that can guide you through that process. And there's a developer portal on SingularityNET website. If you want to help with the actual implementation of SingularityNet, that's in a GitHub repo and is a different thing. And yeah, SingularityNet, it's sort of a different thread than what I've been talking about today, but they're intended to converge together, because I think, for reasons I've discussed at length in many other talks, if we do succeed with some of these crazy ideas in getting further and further toward human level AGI, I think it's strongly preferable if the human level AGI is implemented on a decentralized framework rather than a centralized monolithic framework, both for open-endedness of intelligence and for practical reasons, like it stops companies or malevolent governments from eating the whole AGI while it's in a learning phase.
Okay, basically we ran out of time already, so maybe we should let people have their break, and invite everyone in half an hour and 25 minutes for Neil's tutorial on probabilistic reasoning and pattern mining.
Well, thanks a lot, Alexei, and yeah, thanks everyone. We could go on a long time with these topics, but at least we got wading into the depths a bit, and I hope both for Kevin's presentation and mine, there's a bunch of reading material you can follow up to go in deeper.
So one quick clarification. Nils' presentation is on the other channel, room 1, in 25 minutes. So, and thank you,
yeah,
Ben
I would
and Kevin.
say, regarding the last question, as well as SingularityNet, if anyone is interested to get involved with OpenCog, which is one of many cool things you can build on SingularityNet, and interested to sort of contribute your vision and thinking or your engineering prowess to helping us build Atomies 2.0 and a new version of OpenCog, you can also contact us and join that club as well, which overlaps with but is somewhat distinct from SingularityNet. So yeah, thanks everyone. See you in 20 minutes for the tutorial.
Thank you.